right, let's get started. Hello, everyone. I'm Dan Filestra. I'm the founder and president of Frontline Systems, website solver.com. And we're going to talk about leveraging your code and your users' investments, actually, with a series of APIs and about how those APIs change. So here's what we'll cover in this session. First, we're going to talk about leveraging your code, and I really do mean reusing as much of your code as you can over time. Now, technologies do change, APIs change, and you will have to write new code to deal with those APIs, but if you approach it right, you can leverage a lot of your code across those changing technologies. We'll be talking about that. And one of the obvious ideas that I just want to make sure everybody thinks about is creating your own layers of abstraction and using your own internal APIs consistently. An even more important issue in many ways is preserving your user's investment in your app. That is, almost any application, this goes well beyond like Excel or Power BI or any of the things we'll be talking about. Your users put a lot of effort into your app. They may use it to create and store data, and the way that you store that data and the ability to recover it later is important. Your users may create code or scripts or something like that. In our case, people are building, in many cases, very ambitious workbooks with lots of formulas in Excel, and we want them to be able to, that's an investment they make that we'd like it to pay off for them over time. And we're talking about a lot of time. You'll see that there's a sort of a 30-year recap here where we've been able to preserve some users' investments over that whole 3-decade period. There is a focus in this session on Office.js and REST APIs for Excel, because the new release of APIs is very topical and has enabled some of the things that I'm showing you in this session. But we'll be talking more generally about how you approach things as a developer. So the story here is ours from Solver in 1989. Now this is really a long time ago, 30 years ago. At the time this was done, Lotus 123 was king of the hill, and Microsoft was a relatively small challenger for Lotus, and Windows 3.0 had not yet been launched. It was launched in 1990. And so the diagram on the left of the screen here is actually from the spec that we and one of Microsoft program managers wrote in 1989 for what the solver would look like. And one of the reasons we wanted to do this is because Lotus, king of the hill, had this solver in Lotus 123G way back at that time. Over on the right is actually a dialog that still exists in desktop Excel. There is still a version of this solver available in desktop Excel, but nothing like this is available in Excel Online. However, something better is available in Excel Online. It looks like this. This is Analytic Solver. Actually, there is a free solver app in Microsoft App Source from us that you can use in Excel Online. But this is a picture of this full Analytic Solver product, which is a very large and ambitious product that does everything that Solver did, squared and cubed, and lots of other things, Monte Carlo simulation, data mining, forecasting. Actually, a full suite of machine learning capabilities is all in there. And not only that, but throughout this journey, in the process of doing what we're showing you here, we built out something on Azure, which we call a RaiseOn server. I'm going to dig into this a little more. And because we did all this work over the last few years, we have more than 500,000, about 550,000 cloud spreadsheet analytics users, most of them on Excel Online, some of them on Google Sheets. But we've been able to do what we've done because we have this Azure hosted service. So let me switch to a demo machine here. Make sure that comes up, and show you a real quick demo without explaining very much of how this works. We're going to dig into that at a later point. But what you can see here, first of all, is an Excel workbook with a model, and it's a solver model. Notice that it is in the browser. This is Chrome, so we're running Excel Online. And the problem we're solving here is the classic airline crew scheduling problem. That is, I've got crews starting out at 3 different cities, Salt Lake and Dallas and Chicago. I've got a number of flights that I need to cover with working crews. But when a crew flies from one city to another, then they're in position. They either have to work on a flight to somewhere else, or else they have to travel as passengers to somewhere else and get back home at the end of the day. So looking at this Excel model, the decisions we need to make are, which paths. So what you see in each of these rows is called a rotation. Like the first one is the crew acts as a working crew going from Salt Lake to Dallas and again going back to Salt Lake. And the second one, they are working from Salt Lake to Dallas and then they fly back as passengers from Salt Lake. Over here, essentially I need to have one crew, exactly one crew, on every flight that I'm flying. Now this is a regular spreadsheet what-if model, so I can turn these things, I can make the decisions and say, all right, we'll put that crew on there and we'll just pick the first choice for the Dallas crew and the first choice for the Chicago crew, and we get something, we get a cost to the airline of what we're going to pay these people, but we don't really have what we want. There are zeros, meaning we don't have crews on some flights, and we have two crews on one flight, so that's not a good idea at all. So so the problem here now that we're going to try to solve is to find the optimal set of choices here, so that all the flights are covered, and we do so at minimum cost to the airline. So we've set this up already. We're saying we want to minimize this cell that computes total cost, and we want to change these. We want to find values for these cells here, and the main constraint is that we want all these cells to come out to be exactly 1. So we can do that by clicking here, and this now goes off to this cloud server, brings back a solution, plugs it into the spreadsheet here. So you can see that we have now covered all these flights. So this was just a calculation on the spreadsheet at the end. All the flights have exactly one crew, and we have minimized our costs at $8,775. So that's the sort of thing that Solver does, and we'll dig into that a little bit further. But now let me actually go to Analytic Solver on the ribbon here, and just talk about how we would actually use this. I mean, it's nice to see this as a spreadsheet in Excel, but to use this in an operational sense, we would have to, like get these assignments out to the crew, right, through an operational, business system of some kind. So I'm going to show you a little bit of magic here, I think. Two things. One is, this is an Excel, and it's bound pretty tightly to Excel, and Excel is not so easy to carry around in an operational business system. So the first thing I'm going to do is I'm going to take this model, the Excel model, and I'm going to turn it into something independent of Excel, which is a web page. And so it's just created that web page, and McAfee wants to scan it for security. But then let's just open this page. Now it's boilerplate HTML. Something about the Excel model is appearing in this upper pane. And there's a button here. You might say, well, maybe we can we solve this model even though it's only a single standalone web page? So we'll go ahead and make that request, and sure enough, if you can see down here, we get back a solution to the problem. The solution's coming back in JSON, but if you recognize those assignments, we have the same crew assignments in this standalone web page. So now if I had that, so somehow I'm solving this model completely outside Excel through a standalone web page. Could be the basis of a mobile app. But now, how are we going to get this out into the field? So again, I'm just going to show you this right now without explaining it too much, but here I am in Microsoft Flow, and I have a little flow that's going to use a sort of hosted version of that web page, and I'm going to notify the crew. And we'll look at this flow a little later, but right now we're just going to run it. And all it does is it actually references the results of that model, of finding that optimal solution, and then it sends emails out through the Exchange server. And since it sent an email to me, and I am, this is my real live email, you can see that this email just arrived, and these are my assignments for the week. So all that works, and we're some distance away from desktop Excel. Okay, so switching back. So let's talk a little bit about how we made all that happen. But there's more. So first, I want to just give you an idea the depth of the interaction between this add-in and Excel. So Excel is sort of a substrate for a pretty powerful and general application. So there are things like the ribbon and the task pane that you saw, but then there are custom functions, which we'll illustrate in a minute here with a Monte Carlo simulation example. There are events that happen when the user is just changing numbers on the spreadsheet. We're reading and writing cells. We even get the whole workbook contents and create new worksheets. All those things are things that this application needs to be able to do, and so it's interacting with Excel in many ways. And to sort of picture that, here is that model, and I've got the ribbon visible, and you can see there's a drop-down menu, and there's the task pane with quite a bit of UI in there. And then there's a pop-up dialog that's on display, but that's not all. So here's sort of the rest of the things that are happening. There's a custom function on here. This is the airline revenue management problem. We're reading, writing cells, getting workbook contents, and so on. Now, the thing is that these APIs have changed over time. In fact, this is sort of a history showing you what has happened in the last 30 years. So the very first version of Solver was built using something called Dynamic Data Exchange, DDE. And I don't think there's anybody here left who has ever worked with a DDE. Some people might recognize the Excel macro language because there's elements of that still around if you build an XLL function, right? So we'll illustrate that. And then about 1993 is when COM and VBA came into the picture. This was all a 16-bit world at the time. Then we moved to 32-bit COM and VBA. Other things happened. We eventually went to the XLSX format. We went to 64-bit COM. And finally, in 2013, we had the first version of the Office.js APIs. And we actually built and launched the basic solver, much less than all of Analytic Solver. By the end of 2013, we were shipping that. So we've actually been at this, this JavaScript add-ins thing for like 6 years. If you're just starting today, you have a lot of catch-up to do. So there's a lot of history here. And so I'm really going to be talking about how we leveraged our code and our users' investment over all this time. One observation is that you could take a model from Excel 3.0, the Solver model in a workbook, and run it today in Excel Online or in this Analytic Solver application, and it would work, completely unchanged. Okay, so how do we make this happen? The issues are, and this is going to be true for almost any developer, we have lots of computational code. And then we have lots of user interface code. We're going to find that as the technology changes and the architecture changes, we have very, very different ways to run even our computational code that's independent of any APIs or any UI. So we're going to run it in process, out of process, and so on, and in the cloud. Then we have these APIs that have changed over time. Then we have, in addition, the fact that we've got to make this all work in an environment where, so Solver was, it's been around for so long, and it's appeared in many textbooks, and it's been used. There are literally millions of Solver models out there on the web and so on. And we actually, people would be mad at us if these things did not work. So that's part of our challenge. So this is sort of like the takeaways from the beginning, and we'll come back to like this sort of summary slide a couple of times of the big lessons that we've learned that I think you could apply in almost, not just in Excel add-ins or things for Power BI, but in almost any project, because almost any project relies on others' APIs. So first thing is use but don't depend internally on others' APIs. We'll talk more about that. Define and consistently use your own internal APIs. Segregate and generalize your computational code. And then think about how your users' work is persisted and think long-term about that. Leverage open standards, leverage other popular APIs. The Excel Workbook API is an example of a proprietary but very widely used object or storage format. And then plan how your users' work can be used beyond the initial conception of your own software. And you can see that we're able to do that and get some very big benefits, like what you just saw with Microsoft Flow. And then if we have time, talk about leveraging your development team over time. And that's sort of more of a development management issue. So a little bit more background on what Solver is. It's used in many different applications. It's very much a horizontal or cross-industry application. So these are some examples: choosing lowest cost shipping routes, maximizing returns from stock portfolios, going all the way down to minimizing damage from a radiation beam aimed at cancer, aimed at a tumor, and trying to strike the tumor cells and avoid all the normal healthy cells to minimize the damage. That's actually an optimization problem that is used in practice. So what these things tend to have in common, you'll notice, minimizing and maximizing appearing again and again, and choosing, or similar words like scheduling and allocating resources. And that's the nature of an optimization problem. And if you Google on optimization problem, you'll get something like this on the web. And so this is just from a web page. So what we're doing is we are choosing values for a set of decision variables, x1 to xn. And we have certain constraints that are functions of the decisions that we make. These are things like we have limited inventory, or we have only so much dollars that we're going to allocate to a stock portfolio. We have only so many surgeons in operating rooms, and so on. And then there's something we want to maximize or minimize, like maximize profits or minimize costs. So think about this in spreadsheet terms. The x1 to xn are going to be input cells, numeric cells on the spreadsheet, and f of x and g of x are going to be formula cells. So if we look at a worksheet here, this is a different kind of example, the so-called product mix example, where we're trying to make 3 different products, TV sets and stereos and speakers, out of a set of common parts. And so the effect we want to achieve is x1 and well, I can just put it on the worksheet on the display like this. X1 to x3 are the decisions we need to make, how many TVs and how many stereos, how many speakers to make. And then we have formula cells that are constraints, where we simply compute how many parts get used when we make certain products. And then we have something we want to maximize, which is profits. So I just want to make sure you have in your mind what an optimization model is all about. So let's talk a little bit, look at some code. So one of the things we obviously have to do is retrieve values from cells. And in a moment, we'll retrieve formulas from cells. So in C++, this is a little code fragment that shows how we used to do this. And let's see, do we have people here who recognize something in this code, like XLLs or XLMREFs? We got a few people, yeah, sure enough. So this goes way back. You can see the date, 1994. That's when it was actually copyrighted, written a few years earlier than that. This is very old code. It's actually a real credit to Microsoft, I think, that this code still works in desktop Excel for Windows only, but it's been usable for many years in desktop Excel. But this is useless in Excel Online. You can't use this code at all. There's no Excel operators. There's nothing like this. So that was 1994. So let's jump forward by, let's see, 14 years to 2008. And now we have some more code. And there should be some people here, maybe a few more people, who can recognize like dispatch pointers and variant types and stuff like this. So this is COM. And this is, of course, using COM from C++ instead of using it from high-level scripting language like VBA. But this code is doing almost the same thing. It's retrieving the formulas instead of retrieving the values from a possibly a multi-area cell range on the worksheet. Now, the code that we saw a moment ago was usable for a long time, but not usable in Excel Online, and that's true again here. Okay, this code that we can still use it, but only on desktop and only for Windows. Not useful in Excel Online. On the other hand, let's look at this code, which is from even earlier, 1991. This is actually the top level. Completes the complete function call, but calls a bunch of major functions like phase 1 and phase 2. But this is the original code for the simplex method for linear programming that was in the Excel solver, way back. Someone from Microsoft saw this and said, "Dump Tableau. I don't know if you should say that." And so just to explain, the Tableau is something that's in linear programming. It's a matrix of coefficients, and it has nothing to do with Tableau software, the company, and that sort of thing. But the interesting thing about this code is that this code is fully usable in Excel Online. And why is that? I mean, you can probably guess right away that It's pure computational code, and there are no API dependencies in here. So now let's jump ahead in time some more to 2015 and look at some newer code, which is this is now dependent on the newer Office.js APIs, and there should be an await in front of xl.run. But the point I want to illustrate here is, first of all, this is pretty clean code, and it's one of the nice things about the current JavaScript APIs. And you can kind of guess what's happening here. If you're at all familiar with Solver, it will produce something called a sensitivity report, and that's what we're creating here. And you can see we're putting out the title, and we're saying what Solver engine was used, and we're beginning to format cells and so on. But we're getting the data to populate this report from an internal API. And so where we're referencing app.results.objective initial value 0, that's I think obviously a JSON reference, right? And we're just dereferencing something that's part of our internal API. So that's what I'm trying to illustrate here is that establishing and consistently using your internal APIs is a very good practice. So one other aspect of this is preserving users' investments over time. I want to make sure this machine doesn't go to sleep on me. There we go. So again, users have created millions of workbooks that have solver models in them. And so what we did is there's a bunch of information we need to have about the structure of the model, and we essentially serialize that. We extend the Excel workbook format through the facilities that are there, and we persist the information about, like, this is a simple thing you could try yourself. If you go into a cell that has a solver model in it, and you type equals solver_pre in a cell, you'll get the precision value, all the way from the basic Excel solver up to the present and analytic solver. Now, some of the ways that things are stored are more subtle than that, but this one is fairly obvious. But that has paid off over time for a really large number of users. This is why a solver model still works today, 30 years later. So recapping stage one. So we've been able to make it so that our computational code, the things that they actually do, like the simplex method or the GRD nonlinear method for optimization, we've been able to reuse that over many versions of our software products. And we've done that by isolation, right? And by using internal APIs. So we have something called the Solve API internally. I'll tell you that we haven't been perfect, and there are times when we haven't fully consistently used our own APIs, and we've sort of reached around those internal layers, and we've paid a price every time for doing that, but that is certainly a good practice. And then thinking about, I think the most important lesson I can convey here is thinking about what is going to happen to your users' investment in your software, users' data, your users' models, or whatever, and really think long term about that. We've been able to, it's been very advantageous for us to leverage the Excel workbook format. Okay, now I'm going to go quite a bit deeper here and get a little more technical or a little more mathematical, I guess, and sort of take this to another level of leveraging code over time. So something else that we do in Analytic Solver is we do Monte Carlo simulation. Now, some of you may be familiar with this, some may not, but the basic idea is very simple. We have quantities in a spreadsheet model, or it could be a model in a different kind of language, but there are uncertainties we're dealing with. Maybe uncertain interest rates, maybe uncertain arrival times of people coming into bank tellers, or uncertain arrival of calls in a call center, all sorts of things like that. And we want to model that situation and first of all, just understand this range of things that can happen. That's what you get from Monte Carlo simulation. And then typically we want to do something about that to mitigate risk, or to maybe even take advantage of the uncertainty. And that basically, what we're going to do is we're going to have certain inputs that are drawn from probability distributions. So they're not fixed numbers, but they are drawn from a certain distribution of numbers, and we're going to calculate the model thousands of times. Okay, so this is an example of a model where we do that. This is where we have custom functions. So we have a distribution where we're actually drawing from the number of no-shows. Let me actually switch to this other computer and show you. So this is that Monte Carlo simulation model, and in this cell we have this function called psi log normal. And if we actually double-click over here, it sort of will depict that probability distribution. We're going to sample from it. And then down here, we're interested in that total revenue value. What the model basically does is it simulates a flight taking off many times when some passengers are no-shows. You know, they have a seat, but they don't show up, and they kind of want to get the value of their ticket back. And so we could oversell the flight, which we're actually doing here. We're overselling by 10 seats. Or we could sell only that many, and we can explore what happens across not just one takeoff, but like 1,000 takeoffs. So to just show you what happens when we run this, the idea here is we're going to say we want to run the simulation for 1,000 trials, drawing different samples every time for the number of no-shows. So we're running this again in Excel Online and going out to a remote server, and that was 1,000 Monte Carlo trials coming back here. And I want you to think just for a second about what would have happened if we had, how fast this would be if we were trying to make Excel recalculate 1,000 times. I mean, that wouldn't be challenging. And just to underline that a little bit, I'm just going to go into the parameters here, and I'm going to change it from 1,000 trials to 10,000 trials. So now it's 10,000 trials, and we'll just run it again to see how much longer it takes. And it doesn't take any longer at all to speak of, right? And so we're going to talk a little bit about how we achieve that. And that leads us to other ways that we leverage our code. So the primitive way to do simulation in Excel is to calculate over and over again, make Excel do that. And the issue is that Excel is an interpreter for a language, the Excel formula language. And an interpreter is, anybody ever written an interpreter or compiler? Maybe not. But if you think about this for a while, it takes longer to figure out that there's A1, and there's a plus sign, there's B1, and we're supposed to add them, and then get those two values, and then actually do a floating point add. The overhead of doing that is about an order of magnitude. It's about 10x. Interpreted code is usually about 10x slower than compiled code. So Excel is an interpreter. If we ask it to calculate 1,000 times, it's going to interpret and calculate 1,000 times. So if we could do something about that, and specifically what we did is we built our own interpreter for the Excel formula language, so we can look at and interpret the formulas. And since we know we're going to do a Monte Carlo simulation, and we're going to do exactly the same calculation, but with different random samples, 1,000 or even 10,000 times, we can interpret once, calculate 1,000 or 10,000 times. And by doing so, we actually, the end user experience speed up is like 100x. It's like 2 orders of magnitude. So this is what we call the polymorphic spreadsheet interpreter. And I won't elaborate too much on where that name comes from, but I'll show you a little bit of code. So this is actually the function in C++ where we're, because we have our own Excel interpreter, and this code, by the way, is independent of any Excel API. We're actually doing this calculation, and right at that middle point where it's pointing, where there's a for loop, int fi equals 0, fi less than n forms. So n forms is the number of top-level cells that we're going to look at, that we're interested in getting results of. And if you think about that model, which I can probably just depict for you over there, there's actually only one cell that we want the top level, the value of, and that's the total revenue. So that loop is going to be executed one time. Okay, and then in the middle of that loop, we're going to call this eval_real_vec function, which is going to essentially do an array evaluation of all the formulas in the model one time, much faster. We actually have code here where if this should fail because either the user interrupts it or we get run out of memory, then we fall back to conventional Excel calculation. And if you can see on the very bottom line there, we have for int ti running from 0 to n trials, and n trials might be 10,000. So the fallback is much slower. But now the real part of the point here is that this is code that we can use that doesn't depend on external APIs of any kind. Now it turns out that optimization, and here I will have to gloss over some of the math of it, if you will, but But optimization has this problem in a much bigger way. Okay, so the problem with optimization, and I can see that somebody in the Microsoft people who handled my slides changed some words, but we'll overlook that. Okay, a primitive way to do optimization in Excel is to calculate over and over again. An effective way to do it is, again, to interpret formulas. So the issue is that optimization is a search for the ideal, the optimal combination of values of possibly, a few dozen cells, but it could be hundreds, thousands, or for some of our current customers, it might be 1 million or 2 million different decisions. Every one of those represents a dimension in a multidimensional space that we're searching to find the ideal combination. So doing, just asking Excel to calculate over and over again and wandering around is not an effective approach. An effective approach is to interpret the formulas, and then when we compute values, we're also going to compute gradients, derivatives or gradients, which are going to tell us the direction in which things are changing as we adjust the decision variables. And it also by looking at the formulas algebraically, we can actually learn some more things about just how hard this search is going to be. Like over on the left, that's a smooth convex function, really easy to find the maximum. And the middle one is kind of harder because it's a non-convex objective function. We have to search. And then over on the right is the effect of using if functions and choose functions in your Excel model. So you have many constraints, and you end up creating something that is very much like a maze, and you have to find your way through it. It makes it quite difficult. But by interpreting the formulas, we gain a whole lot in our ability to solve these things. So this is another little bit of code from inside the Sci interpreter, where we are computing for an expression like a1 times b1. We're computing the function value in the middle there, where it's kind of pointing at that mul function call. But then just below that, we compute the gradient of a1 times b1 with respect to all the decision variables by calling this other function. And the advantage here is, again, like orders of magnitude speed. If we have 1,000 decision variables, it's roughly 1,000 times faster. If we have 1 million decision variables, it's not even worth talking about. It's many, many times faster. So this is something that we do inside our code. Now, all that code is leverageable across time, and it's been worth our while to build this whole Sci interpreter, because we've been able to use it over many years, actually. And Frontline has about 9,000 plus organizations and several 100,000 users as customers. But notice also that in addition to sort of leverage over time, we're getting this ability to run optimizations and simulations anywhere, not just inside of Excel, not just on the desktop. So again, we used but we don't depend internally on things like the JavaScript APIs, either the COM or the JavaScript APIs. And we've pretty consistently used our own internal APIs. So we've gotten this far. Now we're going to sort of shift gears again and look at what happened. How do we deal with the issue that we're going to run this computational code in very different ways? We're going to run it in process in Excel for Windows. We might be running it. We used to run it out of process in Excel for Macintosh. And then we're going to run it in the cloud, as you just saw with Excel Online. So now we're sort of stepping up to the sort of architecture level, and let's look at what we have here. So you've kind of heard about, we have these optimization algorithms. We actually have 12 or 13 different optimization solvers, and then we have a simulation engine and sample generation, and then we have all these data mining algorithms too. We're kind of leaving that out of this talk. And then we have the Sci interpreter that is able to analyze and interpret Excel formulas. So that's sort of the picture if we just looked at Excel, but we have a little broader view, and I'm just going to introduce these other elements. In addition to defining your model in Excel, we let our customers define their models in two other ways. One is in this high-level modeling language we call RaiseOn, which we're going to talk about a little bit later. RaiseOn is an acronym for Restful Analytic Solver Object Notation. And we'll talk about that for a minute. And then the third way that you can define your model completely outside of Excel is in code, in C++, C#, Java, R, Python, where we essentially expose a high-level object API. that you can use to define decision variables and constraints and uncertain variables and things like that. Okay, so now one way that we physically, this is sort of the general architecture independent of any physical packaging. So here's the first kind of physical packaging. We have these SDKs, Solver SDK and XLLiner SDK, where we expose things through an object API. And if I shift over to the other machine here and bring up Visual Studio, here we have this is a set of little sample applications in C# that we can compile and run. And each one of these is this is a little app that does one clever thing, which is it reads its own source file and then scrolls around when you're running these examples to show you the source code that it is running. So if I actually go to, let's say, second example here, and this is a small linear mixed integer problem, and you can kind of see the objects. Hopefully that's reasonably readable, where we have vectors of decision variables and vectors of constraints. And we can run it, and this will just yield an integer solution for just a couple of variables. But the example that I'd like to show you that's more interesting is, scrolling down the list a little ways, is this one where we're going to run some C# code. And all that C# code is going to do is instantiate a problem in our object library and then say problem.load. And it's going to load an Excel workbook. And the result of that is to instantiate in our object model the formula, well, the objective and constraints and everything that is actually in the Excel workbook. And so then we're going to actually solve the model and then output these lines, optimus status and objective. So I'm going to actually open, let's see, the one I want. Let's think about the one I want. I'm taking a little bit of a risk here. Go ahead and try this one. But it runs. So this is that airline model, the same thing we were talking about before. The constraints all come out to be 1, which is what they should. That means the flights are covered, and the solution is the same, and the objective is the same. So what's happening there is, if we go back to the slides, the SDK looks like this. So it's got the sign interpreter, common code, optimization algorithms and simulation algorithms, common code. It exposes that object API. And it also has the ability to load in an Excel workbook and interpret it through the sign interpreter. So that's the whole thing. It's just it's a DLL, solver SDK.dll and XLLiner SDK.dll. But so now, what happens? How does the architecture change when we're dealing with desktop Excel and COM? Well, it just kind of looks like this. So many of the same elements. Sign interpreter's there. All the algorithms are there. Instead of our object API, we're now using Excel's API, the COM API and the XLL API. We use them both. And we talk to desktop Excel. And our model comes from Excel, and our data comes from Excel. And then we also have UI code to create a ribbon and task pane in COM and using like VSTO and COM and C# and all that. Now what happens when we want to move this to Excel Online architecturally? Well, it kind of looks like this. So we take the sign interpreter and the optimization algorithms and we move them to a remote server. And we put a REST API in front of that remote server. And the interesting thing is that what the server is going to do is it's going to receive an Excel workbook model and it's going to run our Solver SDK, just like we just did in Visual Studio. We're going to run that on a Azure backend worker. Okay? And then we have the actual JavaScript add-in uses JavaScript APIs, makes calls to to office.js, and also creates all the UI, the ribbon, task pane, and so on. So it's really HTML, CSS, and lots of JavaScript, talking to Excel. And the especially nice thing about this, which is so much better today for all of you than the way things were years ago, is that this code, this JavaScript API code, is itself leverageable. So it works in Excel Online, which is the new possibility, but it also works in Excel Desktop. It works in Excel for Windows and in Excel for Mac, and actually in other devices like Excel for iPad. So that's a real advantage. So about that REST API, so we have this server called Raceon. It is a, I can actually show you on the demo machine, just in the browser. This is Raceon.com, and this is simply a developer portal, a front-end portal where you can exercise a REST API. And we have a little editor in here, and then we have a bunch of API calls that you make. I'm going to actually run something different here, product mix 4, just to show you an example of a Raceon model. It's like the product mix we were talking about earlier. And so this literal payload, which is JSON, Raceon is embedded in JSON, defines the product mix model very much like we were looking at in Excel. And we can send that off, just that is the payload, that literally is it. And then it comes back from the Raceon server with a JSON response, which tells us that we should make 200 TV sets and 200 stereos and no speakers, and tells us things about the constraints and so on. So that's what the Raceon API looks like. Now, so and this has allowed us to to support all these 550,000 cloud spreadsheet analytics users for both optimization and simulation. So here's a little bit of code from within the Raceon server. This is really from one of the back-end workers. So this is in C#, but all it does, and it's using Azure APIs. This is obviously dependent on Azure APIs because it's reading from an Azure queue, and then it gets a reference within that Azure queue to an Azure table, and from the table it gets all the details about the problem that it's going to solve. Excuse me. And then it instantiates and calls solver SDK. And then it's going to take the results and put them back in a place where they can be sent back through the front-end API. So that's just to give you a flavor of what that's like. So at this point, we have leveraged our computational code. We have leveraged our Psi interpreter code. We've also kind of leveraged our solver SDK, something we built for other developers to use by ourselves, because we're a developer and we want to build this Raceon server. And now we have something even better. Because of the JavaScript API, the modern Office.js APIs, we have common UI code as well for Excel desktop and cloud. And we've done this in the ways that we have already talked about. Okay, now we want to help people. We've helped our users preserve their investments and continue to use their investments, but we'd like to go further. We would like to enable them to leverage their investments. So they built they built this elaborate model in Excel, and we want to help them leverage it outside or beyond Excel. So how are we going to do that? So the first question is, what would our users like to do above and beyond Excel? So one thing is they would like to, you build a model. A typical situation in a large organization is, some analyst builds the model and figures out, how to solve the crew scheduling problem. And at a certain point they say, well, we're going to try to we're going to put this into production. So they bring in a developer, and the developer looks at this Excel model and says, well, I don't know, I can't work with that. So I'm going to start over. I'm going to write the thing in code and call some library. Hopefully they call our solver SDK, because then they can just load the Excel model. But you run into that kind of situation. So you'd like to make it, you certainly want to enable that scenario, and that was one of the first scenarios we did enable. You'd also like to deploy models for client-side custom applications. And if you recall a minute ago, we were sitting in Excel online, and we said, create a web page. And we created really what is a skeleton web application, a single-page app, which can also be the basis of a mobile app. And we're interested, I'm going to talk about how we do that. But both of those approaches require us to write code. And people, would rather have low-code or no-code solutions. So we're going to talk about doing that too. And I want to show you how we can deploy an Excel model, just point and click, into Power BI where it can run. And we can take another look at that Microsoft Flow example and see exactly how that little bit of magic happened at the beginning. So about Raceon. So Raceon is, it stands for RESTful Analytic Solver Object Notation. It has two key attributes. We work in a world where there's other vendors of optimization and simulation and data mining software and several of them offer high-level modeling languages. So Raceon is our high-level modeling language, but the way it's differentiated from all the other modeling languages is twofold. One is it contains the entire Excel formula language as a subset. Raceon's sort of on the level of MATLAB, if you've ever used something like that. And if you had ever come from like our domain, you would hear about things like GAMS and AMPL and AIMS and so on. These are high-level modeling languages. But Raceon is a similar high-level language, but you can do essentially anything that you could do in Excel, use all 500 Excel, or whatever the number is, built-in functions in Raceon. And the second thing is that Raceon is embedded in JSON and valid in JavaScript. So if we look at just a little segment of a web page, and it's doc type and HTML and head and script, and then we drop into JavaScript. We start writing some JavaScript. We actually define something we're going to use, the server endpoint. And then we say Raceon model, open brace, and the rest of it is pure Raceon, because Raceon is JSON. It's all a valid constant. And inside Raceon, you can see things like sum product, D9F9, mmult, D11F15. That all works, because Raceon contains the entire Excel formula language. You can also actually write Raceon without using any reference to Excel. So this is actually that airline revenue management model, the model with no-shows, the simulation model, written out in Raceon, not referencing any cells, just referencing symbolic names. So you can do that as well. So let me now actually show what happens what we get out of this. And a key point is that we can translate from Excel models into Raceon models. So let's go back to our airline crew scheduling example. We ran this in Excel Online. We could run it in Excel for Windows, and then we ran it through Solver SDK. But now, and we actually turned it into a single web page that was sort of standalone. We can also just say create app Raceon.com, and all this does is pretty much generate the model and then load it into the Raceon editor so that you can use it and run it directly from here. But what we want to do now is another option that you may have seen on that pull-down menu, which is create app Power BI. Now the only thing is that this takes about a minute. We're running these different Microsoft tools and Node.js and so on, and it takes a minute, and that's an agonizing amount of time when you're live presenting or watching. So if you'll bear with me, I've done that step already, create app Power BI, and that creates a PBI viz file. It's what Power BI calls a custom visual. And so we're going to go into a Power BI worksheet here and make sure we're still alive, because this has been sitting here for a while. And we'll edit this report. And I'll make one point. Let me actually bring up Desktop Excel for just a second to show you. This is that same model in Desktop Excel, but I've got one more thing in here, which is I'm marking certain cell ranges as things I want to be able to change when I'm in Power BI. So this is data binding from Excel into Power BI. So now I'm going to import that custom visual. So we'll import it from a file. It's on this local machine. Of course, it'll warn me that I'm importing code. And let's see, I do want this one. So we're importing a custom visual. And I'm going to run it, and I'm going to show you what's inside that custom visual. So it's on the palette here. So we'll click it and bring it onto the worksheet or onto the canvas. And you can see that in the well, it's asking for data, right? Won't do anything until it has data. This is a live model. This is not like going to be a static rendering or anything. It's a live model that will change. And so I'm going to drag in the routes here, so it has that, and then I'm going to drag in crew cost. It has there, and as soon as it has it, it goes off. It makes a REST API call to the Raceon server, saying I've got an instance of this model. I want to solve it, bring the solution back, and then graphically represent it. And if you think about what we had in Excel, it's the left-hand chart is just ones and zeros, so those are the selected routes. And over on the right, we're covering all the flights, right? All the constraints are satisfied. And just to show that this is truly a live model, if I take away that crew cost, and then I'm going to substitute the other data set that I have here, put that in its place, it will run again and come up with a different optimal solution where we've rearranged the selection of the routes. So that's something nice that you can do in Power BI. And let me actually switch back here, so you saw that happen from Excel to Power BI. Now let's talk a little bit about going from Excel into a business process using Flow. And this picture is sort of a general purpose picture. I actually got this with permission from one of the Gartner analysts who's talking about this. At the bottom is sort of a generic, it's actually an order fulfillment business process, which might include automated steps and manual steps. And at a certain point, we're making a decision to accept or reject the order, and we might do that in an operational business process by putting something on a screen in front of somebody who makes that decision, on the, in the order entry center or on the, on the shop floor if it were a delivery-related thing. And we could show that in Power BI or in Tableau. But we can also make this fully automated. In some cases, we could just decide based on criteria to accept or reject the model based on use of an analytic model. So what we were doing in Microsoft Flow a moment ago was sort of like this. And what I'd like to do now is just show you, back on this machine. Here we are in Flow, and this time let's look inside this flow. It's extremely simple. So we're editing the flow, and it's only got 3 steps. We manually trigger it. This is the sort of magic part. We invoke an instance of this Raceon model, and actually if I go back here and find that same instance, it's one of my oldest ones. It's this one right here. This is an instance of this, airline crew scheduling model. So I'm referencing this here, and the magic of Flow is that we built a very simple custom connector around our RaiseOn REST API, right? And so the magic of Flow is if we go in here and actually create or edit this step where we're going to send an email, Flow knows what comes back in JSON in the response and will tell us, oh, would you like the status, or would you like the objective total final value like we already have here, or whatever you want, you just click and it will appear in this in this flow. And so if we actually test it again here, and I'm going to perform the trigger action manually, of course. We'll let it run. It's just going to do the same thing again. But now we can actually look in Microsoft Flow. We can look and see what happened. This is the most recent instance. And we can actually see what happened at each step. So like in here, we can actually see that the result came back, and we can actually see how it composed the email down here. So those are some of the nice things you can do with Microsoft Flow. But at a more general level, we have found ways to leverage our users' investment. We've enabled them to get from Excel into Power BI and Microsoft Flow and other things in a much faster, effective way. Okay, so we've done these things. We can say that solver models from way back in time still work. Risk solver models, our earliest Monte Carlo simulation models still work. And they work not only in Excel, but in Power BI and Power Apps and Flow, and also if you want to use them from a programming language. And so we've done this by being careful about thinking about how our users' work is persisted, and leveraging XML and JSON, of course, and then leveraging the XLSS storage format, which has been good for been good for several decades. And then we thought a lot about how our users' work could be used beyond Excel. Now, of course, we didn't foresee everything. We couldn't have. But I think you could apply these principles to just thinking about it and trying to structure your work to make this possible. So just a few closing comments here about how do you leverage your development team across changing technologies and changing APIs. So the questions are these: how does a small team write and maintain so much software? My developers don't like it when we talk about lines of code. I mean, nobody does. In fact, they're proud of the fact when they refactor code and it shrinks and you get fewer lines. That's something that we work on. But it's some kind of measure, and it was a surprise to me actually to see how many lines of code we had Much of that is computational code and the 12 different optimization solvers and simulation engine and data mining algorithms, neural networks and classification regression trees and linear and logistic regression, all those things. But how does a small team write and maintain, importantly maintain so much software? How does a team that used C++ and COM learn asynchronous JavaScript? Anybody can do it, but it's a question of, what can you do to facilitate that, I guess, and then how does a team used to shipping desktop software learn to build and run cloud services? So I just have a few simple comments about this, really. Now this one, Keir laughed when he saw this. The first one is, I think it's true of our team. It's a small team, it's like half a dozen people. They're good, and that is actually the most important issue. If you have really good people, everything else becomes much easier. Okay, the second most important idea here or observation is that the team has continuity over many years. I think our average tenure of a developer is something like 16 years. And the shortest one is 6 years and the longest is 26 years. And that has allowed us to build cumulatively. We don't forget and discard a lot of code. We've been able to build it cumulatively. And then finally, we've been willing to invest in early stage technologies. And a good example of this is, using things with the JavaScript APIs 1.0, it was a bit of a struggle. The tooling wasn't all there, and the documentation wasn't all there, and the APIs were pretty limited. But we used them, and we were able to ship products on them. And because we have 6 years of experience and over 500,000 cloud spreadsheet analytics users. Just a comment about development, just a sort of a plug for Azure DevOps. If you're not already using it, highly recommend it. It's what we're using now. And we had to go from old style development to agile methods, and Azure DevOps has been a help to do that. So final takeaways. This is really the same slide that we saw near the beginning. Work to preserve your users' investment, work to leverage your own code, and leverage your development team. So that's it. And let's see, I have 2 minutes and 46 seconds left. And so do we have any questions? Stunned silence. Okay. It's actually, for people maybe seeing this on video later, it's 6 p.m. and we're all ready for dinner, I think. So thank you very much.